Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right. Hello, everybody.
Hello.
How are you all doing? We're, as you can probably see, we're in separate areas right now. Neil's feeling a little bit out of the weather.
That's correct.
Under the weather.
Under the weather.
Not
Out
on
of
the weather.
I'm out of and nowhere near the weather, and my voice probably reflects that slightly. And so rather than make sure Alex has a miserable holiday, I figured I'd try to just limit myself to having a miserable holiday. That would be better.
No. Well, we'll make sure we don't direct too many questions to Neil, but I know that we really enjoy doing these live streams, answering your questions, talking about electrochemistry. It's always a lot of fun, and this will unfortunately be the last live stream that we do until the new year. So if you're in the United States, there are several holidays that we're currently in and are going to be happening over the next few weeks. Most people are on vacation. Universities and colleges are also on break. So research tends to slow down. People take vacations. People need time to reflect on all their echem stuff. And so we will also be doing that too. But still stay tuned to the live stream, the YouTube channel, put notifications on. We do let you know about when a future live stream will take place. That way, in case a question that you asked doesn't get answered, we're able to talk about it. All right, so some questions I know are coming in, but the first question we got is from Adintatsarka 1306. I'm sorry.
Good effort.
Good effort. Just really trying. The question is how to do automated IR corrections. This is a very good question. So to kind of back up a little bit, so there is this. I'll actually share my screen. So to describe this in a relatively simple case, I think most of you are familiar, but just so that everyone's on the same page, if you model your working electrode as a circuit, you can think of it as some kind of charge transfer resistance, and then some kind of double layer capacitance, CDL sometimes it's called. And then there's this solution resistance, just call RU. And we're trying to, and a potentiostat can compensate. This goes to the rest of the electrochemical cell. But we're trying to compensate for this RU value. And so the question of how to automate IR compensation is really a question of the potentiostat that you're using. So what P-stat are you using? Because there's two parts. There's two parts to doing IR, automatic IR correction. So there's two parts. Part one is determining solution resistance or the RU. Resistance. This is RU. So you have to determine that. And then the second part is to apply IR compensation to electrochemical technique or your electrochemical technique, whatever you're trying to do. So there's these two parts you have to do. You got to determine the solution resistance and you have to apply IR compensation to your electrochemical technique. Now, what I'm going to do is I'm going to open up our software, which is Aftermath, just Aftermath Blue. And just to show you, I don't have any data with me right now, but every potentiostat should have, or ideally, it may or may not have it, but ours, Pine potentiostats, depending on which one, will have methods for determining the solution resistance or the uncompensated resistance. There's current interrupt, there's positive feedback, and then there's impedance. Typically, when you have a technique like this, you'll have some parameters, you'll perform it, and sometimes that resistance value, you either have to determine that resistance value from the technique, or a potentiostat may be able to automatically determine what that solution resistance value is. Now, once you have the resistance value within an experiment, say it's cyclic voltammetry, typically there'll be some kind of option, say an advanced option, which will be IR compensation. This would be where you apply it. Now, most of the time you might pick some manual level. You'll say, oh, I measured solution resistance. It was 250 ohms, or 200 ohms. You apply that, and then you put all your parameters in, and then you'll perform the experiment. But there are instances in terms of automation where you can pick automatic, and then you can tell, and what the potentiostat will do is it will take the previously determined solution resistance value and then apply a degree of compensation. And what you need to do is determine what degree of compensation is required. So this is the case when you're doing maybe multiple experiments in a row. The solution conditions may change, and you need to sequence experiments in such a way where you have to retake the solution resistance value because it's changed, and then reapply it to your electrochemical technique through IR compensation. So the answer, if you will, and we'll see if they have it. Okay, we have a comment here.
Yeah, she's using CHI.
CHI. So Neil and I are not familiar, unfortunately, with I used the CH Instruments potentiostat when I was a graduate student, but depending on which CH Instruments potentiostat you have, its ability to determine the solution resistance, I think a CH Instruments potentiostat will have the current interrupt method. It will have the current interrupt method. It should have it. And then within the experimental parameters of a CH Instruments potentiostat, you should be able to set some kind of IR correction to your experiment. And just to, I think CH Instruments does have maybe other techniques for solution resistance, but as a very quick review, this is what I would guess, is you would use current interrupt, current interrupt. I can't spell interrupt. There's 2 R's.
Yeah.
Okay, 2 R's. There we go. Current interrupt. And what you'll do in this technique is there's a couple ways of doing it, but like you usually set a constant current. Let's say you set 100 microamps of current. That's your constant current. And you would charge the electrical double layer, if you will, to a certain voltage. So you charge the electrical double layer to a certain voltage, and then you disconnect this is the point of disconnection. This is time. There's this discharge after you've charged the current, charge the capacitor, which is this guy up here. And so what you'll do is you'll look for what's this difference here? What's this voltage difference? This delta change in voltage. And if you know the amount of charge that you applied to create a constant voltage, and you have this change, you can then associate this with the resistance based on V is equal to I times R. I is this guy, and then V is this difference in voltage or difference in potential, and that will give you what the resistance is. It's a pretty good technique. I'm pretty sure CH Instruments has a way or a method of calculating this. Now, the degree of automation, I would say, is questionable. I don't know whether or not CH Instruments can take that value, store it, because it needs to be stored in your software, and then it gets applied when you're doing, say, a cyclic voltammetry experiment or a bulk electrolysis experiment or something like that. So that's the other thing. But programmatically and systematically in your experiment, that is what you would need to do. So I hope that helps. And then once you do that, once you perform that, that'll allow you to get a good, IR corrected electrochemistry data. So let us know if you have any extra.
I'll just add a couple of points too.
Yes.
Which is the first is that, just like you said, which I'm not really sure either, if CH has the ability to like do the experiments and then automatically retain and know the value for the IR drop or the RU, and then apply it to a subsequent experiment. Because one of the things when you say automated can be as, if what you mean is you discover your RU is 100 ohms or something, and then you do the IR compensated like CV afterwards with 90% or 80%, whatever you're using, but you're having the potentiostat compensate during your subsequent voltammogram, then that's great. But sometimes, like what Alex was saying, is that you want to periodically recheck the RU and see if it's changed, if something about your electrolyte changed or something like that. So if the software or the potentiostat doesn't have a procedure to automatically re-update and recheck the RU, then you won't be able to do this kind of automation. And what you were showing with our software is that we do have that ability. So for example, you could make a sequence of like, I'll just make something up. Like you could do like check RU, do like 10 CVs or something, and then check RU again, and then do 10 more CVs or whatever it is, right? So like you could do 100 CVs, and every 10 of them you check the RU, and you're always compensating for 90% of it. Let's just say. So when you check the RU first, it's 100, so you compensate for 90. And then for whatever crazy reason, your RU went down to 80. Okay, great. Now you're compensating for 72 for those next 10. So like as it goes, it'll just keep on like adjusting whatever. Whereas if you aren't able to do that, you just got to hope your RU doesn't change. So that's that. And then the other thing I was going to add is that, of course, everything you showed with IR current interrupt, is obviously correct. The one thing I would say is that current interrupt is like not the most ideal technique, and the reason is a timing thing, because when you're looking at the current interrupt, what you're looking at, again, as Alex just drew, is you have the voltage applied, or I guess it's actually current, but yeah, you drew current, I think.
Yeah, I drew current as the thing that was being applied, but you're measuring the voltage, so either one's fine.
Yeah, I'm afraid to go back. It's going to crash.
Oh yeah.
So this is voltage or current, right? So you basically have something applied, and then what you're doing is you immediately, it's like releasing the counter electrode, right? And so it drops, but there's a decay basically to zero, right? And I think that's kind of what you see. The current goes to zero and the voltage decays. I think that's how that works, right? The voltage kind of somewhat slowly decays.
It decays via RC, basically, like the
right,
RC time constant. So
So here, and so, right. So what you're doing is you're getting, this is the voltage that's related to RU, where it initially drops. But then you actually have this amount of voltage. Like this is, again, like you said, like the RC, right? But what, this isn't like a perfect world where you can measure between here and here. Right? If I were to extrapolate these points down, this is the key, and this is why current interrupt isn't ideal. The amount of time between these 2 points should be very, very small, this delta T. And your potentiostat might not be able to measure this time difference very, very accurately. So if your potentiostat can only measure, let's just say some crazy, like once every second, right? Well, your actual plot might look like this, current interrupt, and then it's like that. And then you're saying, oh, look, this is my voltage for my RU. But that's not accurate at all, because realistically it dropped from here. And you're losing all of this part here because you just didn't measure fast enough. So the reality is that current interrupt requires you to basically release the cell. What it usually happens internally. Back in the day with analog potentiostats, they used to do this manually. They would literally just disconnect the counter electrode. That's opening it, it's interrupting the current path, and they'd measure the voltage drop as quickly as possible. But the reality is that everything's digitized now, and so the switch inside the potentiostat disconnects the counter electrode. And if it doesn't measure the voltage, like the split second that happens, then you can't get this sort of instantaneous drop here. And what you're going to do is you're going to be measuring some of the drop as a result of the RC. So my impression, I would just say, generally speaking, is that even under the best conditions, there's going to be some inaccuracy associated with current interrupt. I find it to be a little bit of a tricky method to be like super confident about how accurate your measurements are. So again, just like Alex was showing with our stuff here, our potentiostats are a little more ideal, I would say, in that we use impedance to get you the measurement of RU. It's a little more accurate, more accepted method. It's easier, it's non-invasive, and it doesn't require this kind of timing issue as associated with current interrupt. So I hope that kind of makes that clear there.
Yeah, no, I figured, because I also thought, like, I know CH Instruments did not have, I don't think it had I don't know if it had impedance or not when I was a graduate student. So my knowledge is that CH Instruments didn't have it, which is the only reason I suggested current interrupt. But yeah,
it's
EIS is the best way to go about it.
Yeah, for sure. And again, some of this is like, we don't really know 100% of what the capabilities of CHI are. CHIR LMNOP. Anyway, so you might have to look into your specific, the software and what it can or can't do to know if you can do all of these types of things, right?
Yeah. Hopefully that's helpful. Let us know if you have any further questions. So we have a couple more questions. There's some questions from I'm David 16. We can maybe talk a little bit about it, but it's bordering the nature of physics that goes a little bit beyond electrochemistry knowledge, at least from my perspective. Which is, his first question is electricity a wave or particle? I'm not 100% sure. I would, my initial, because electricity, as we understand it, is the flow of electrons, but electrons can be both waves and particles. Like that's how we understand them. That's how we know them. And so when we think about, I'd say, as we think about electricity macroscopically, the way it is, it really acts more like a particle, sort of say. And it's we think about electricity as current, which is the movement of ions over time, and so, or not ions, but charged species over time that moves through over time. which can be an ion in solution. It doesn't have to be an electron in per se. So, so that's kind of my take on it. I think it's ultimately both, but when we get to a macroscopic view of things, it makes more sense to maybe not even think about electricity as a particle. It's really like the flow. It's current, if you will. So it obeys more laws of electricity and not physics, big macroscopic physics, not looking at quantum mechanical behaviors of particles and stuff like that. So that's my thought.
When I was in physics or chemistry class in high school, we used to talk about particles and waves. And they said particles and waves or particles and paves because they're all kind of the same when you get small enough. And the best that I can remember or sort of summarize it is that it's essentially like electromagnetic energy, so to speak, light, radiation, X-rays, right? And any sort of anything on the EM spectrum is a wave. It's not like we don't call it a particle. They're waves. They're energy that moves in a wave with different wavelengths and different energy, right? Obviously, wavelength and amplitudes and whatnot. Electrons themselves are particles. Like for sure, they have a known mass. Like we know the mass of an electron, but because they're so small, they behave like waves. So that's the best way I can kind of think to describe it. It's essentially like a particle that acts like a wave, something like that.
Yeah.
So and as it gets any bigger than that, we sort of move out of the classification of behaving like a wave. Basically, once it becomes, like you said, more macroscopic.
Mm-hmm. Yeah. That's a good question. We did get a follow-up about from Anita Sarkar. I don't know if you want to talk about it before we move on to the next question.
Yeah, that's probably a good idea.
So she says, thanks a lot. It does have impedance now. One more question. How much compensation percentage is acceptable? So this is a very interesting, good, and broad. To a degree, it can get pretty detailed. The way that I think about IR compensation and the quote percentage of acceptability has to do with the risk of overcompensating. So I know this kind of this is a question that leads to like a whole bigger set of questions. But if I get rid of this, we have the same system. I'm gonna see if I can't delete this. Yes, I can. Okay. So what ends up happening in electrochemistry experiments, like in a cyclic voltammogram, for example, if you have a one electron transfer process, and it's reversible, it goes to R, you get this nice let's say it's a reduction reaction, so it goes like this, and of course I'm okay at drawing these. There should ideally be a 57 millivolt peak splitting between the two peak potentials, this guy and this guy. Assuming that the electron transfer kinetics is fast, and for most systems it's fast, this is ideal. When you have more RU, this spreads. This goes this way and this goes that way, and this number goes up. But this is ideal. This is like the theoretical value. So there have been, people have said, oh, well, you want, if you completely 100% compensated for any solution resistance and everything else in the system was good, you should get a value around 57 millivolts. I think that getting this value is nearly impossible for most things, for most systems. So even if you got something like 60, that would be fine. 61, 62, that's also pretty good, especially if you're applying IR compensation. So if you by chance overcompensate, these will move in. You'll start getting weird behavior, right? You'll get values like 49 millivolts. And if you got values like 49 millivolts, you're overcompensating, and that's bad, right? So when it comes to the percentage of compensation, I kind of hate the percentage of I hate's a strong word. Sometimes we get on like huge tirades about things that we hate in electrochemistry. So, but I dislike strongly just the idea of a percentage. I know why we have it, but when you relegate it to just a percentage, what this value is, then you're kind of at the whim of, well, it's just some random value of solution resistance that I don't actually know what it is. And I can get some different value here that's like, it's okay, it's fine. But every bit of RU that's kind of here is taking away, because there's another side. You don't compensate enough. If you don't compensate enough, you might have 65 millivolts of peak splitting. And so it's like, all right, you didn't compensate enough because of the percentage that you used. So you have a slightly bigger peak splitting. The accuracy of your measured potential that you're applying towards the electrode-electrolyte interface or the electrode interface is off by a little bit. So for me, I have personally always found, and this is not always practical, that the closer you can get to getting peak splitting for well-characterized systems to be 57 millivolts, the better. And the use of a percentage, while necessary, is not the indicator that I personally like when doing it. But I would, if I were doing these kinds of experiments and you're doing electrocatalysis studies, I might add, especially if you're working in, say, a non-aqueous system, I might add a redox mediator. I might add a well-known system that doesn't interfere, that I know has fast electron transfer kinetics, and I might see, hey, when I apply 90% compensation or 80% compensation, how does this guy change? If I have 80% and then I'm getting my 57 millivolts, it's like 80% is great. If I'm getting, if I'm doing 90% compensation, but I'm getting like 65 millivolts, then like, oh, that's not good. That's not very good. So this percentage, the other thing I'd mention is that this percentage is only as good as the measurement of the RU that you're making. So you're using EIS should be great. If you were using current interrupt, you might have inaccuracies, as Neil said. You're not getting the whole amount of solution resistance, and that's going to cause some inaccuracies. So that's why I hate using these percentages. You don't actually know what the resistance value really is. But what you want to do is you want to look for the ideal value. And of course, the last thing I'll mention is that when you overcompensate in a CV, and I should have labeled these, I'm sorry, you'll see weird noise. If you like overcompensate, you'll get weird jaggedy. I've seen all kinds of the potentiostat do all kinds of crazy things. You'll get these oscillations that are out there, totally out there. And if you get these oscillations, it definitely means that you're overcompensating. You're using way too high a percentage or something, and you need to go lower. So there's a degree of trial and error involved with the acceptable amount of compensation. But I personally prefer knowing what the actual resistance value is and then applying that value to the point where you get the ideal value for a cyclovoltammogram, which is 57 millivolts. And if you're getting lower than that, then you are overcompensating and your percentage is too high. So that's the real thing. Not knowing anything else about your system, that's what I would say. Keep it at that. All right, let's move on to the next question. We have Murmur Salim 495 says, "Hi sir, please explain when we fit different model for impedance measurements in eChem Analyst 2. Firstly, how will we know which model is best and why?" You want me to talk about this, or?
Well, eChem Analyst 2, is that
I don't know which software that is.
Which one is that?
But still, the selection of the model should be independent of exactly what circuit fitting software you're using.
I think that's Gamry.
Gamry?
Yeah. So different models for impedance measurement. Yeah. So first of all, there's no way to answer that question precisely because, to a large degree, the answer to what the right circuit is depends on your knowledge as a researcher. You have to know something about your system to know which kind of model, and then it depends on what you see for the fit, for example. What your data looks like can inform what model might work as well. And then you use, once let's say you've narrowed down 1 or 2 or 3 different models that you think are appropriate to fit your data, based on, again, your knowledge of the electrochemical system, what kind of interfaces are there, what kind of processes are happening. Is it a resistor capacitor? Is there a Warburg element? Is it 2 RCs? Whatever's happening. Then you can look at the, I think Gamry calls it goodness of fit. It's usually chi-squared. Metrics, for example, how close are the points to the experimental, how close is the fit line to the experimental points, basically. You can use those metrics when comparing 2 or 3 different models. But again, most of the answer to this question is independent of which software you're using. It's the one part of this ever increasing, I'm old, so I hate AI and automated everything. And here's another thing that I also hate. I'm going to go off on my tangent and rail against kids these days things. But, in this ever increasing AI world and automated everything, believe it or not, as a human being and a researcher, you still have to use your brain just a tiny, tiny bit. One of the ways that you have to use your brain as an electrochemistry researcher is picking which models to use. Some follow-up questions here, I think, from this person. So, Secondly, why in every model different value of solution resistance, WD, blah, blah, blah. Okay, so that part of it is somewhat easily explainable. When you are, let me, I could probably draw a little bit and kind of, this will help show you. Of course, I don't know really what your data exactly looks like, and I don't know which model you're using, but I'll try to make an example here. So let's say your Nyquist plot, Z real minus Z imaginary. Let's say it looks something like this, somewhat ambiguous, so it might be not exactly clear what model you should fit it. And then let's say your Bode plot looks like this. Okay, so this is your Bode plot, for example. That's the impedance magnitude, it's the frequency, and that's the phase angle. All right, so your phase angle, probably this is like 0, and this is like minus 90. Okay, so it's probably something like something like that. I don't know. And your impedance magnitude plot is probably like something like that. I don't know. Okay, so don't worry if those are perfectly accurate or not. The point here is that you fit model 1, for example, and let's say you fit this, you know, all right, so a simple one, right? And it fits like that, okay? And you say, hey, look, it's giving me too big of an RC, RU or whatever, right? This RU values, it looks like it's too big, right? Okay, that's not great. And then I fit model 2. I'll just do 2 so I don't do 800,000 examples and keep you here all day. And let's say this is based on what I'm seeing, if what I drew is anything like what you're seeing, this would be a slightly more accurate model. I draw an extra one, basically. Okay, something like this. All right, so I fit this one, and this one I get probably a little more accurate. Maybe I'll get something like this. It's close. Maybe it's a little closer. And this RU is like a little smaller. Maybe the RCT is a little better. Maybe it's a little worse or whatever. The reason why your values are going to be different is because unless you, which I don't know if Echem analysts can do this in our software. Again, you're watching a Pine live stream, so you're going to have to listen to me talk about Pine in our software and our equipment. In our circuit fitting software, you can like focus on just one section at a time. You can lock and unlock certain parameters, so you can like just fit, just get a good fit for this, first, and then you can sort of take out, like you can exclude like all the second half of the data and just fit this. Like you can kind of do it piecewise. Even doing that, whether you do it manually or not, is kind of a pain, but you can do something like that. I have no idea if Gamry's software allows you to do that. I don't think it does, but ours does. So in any case, the reason why your RU values, your RCT value, RCT values, your Warburg values, et cetera, they're going to be different is because the software, for the most part, is not focusing on any one of those parameters. It's not able to do that. What it's focusing on is probably this curve, this red curve. And so what it's doing is it is, for all the frequencies, trying to fit, that's just the green fit, and this is the gray, whatever. So you can see I'm not doing a perfectly good job, sort of on purpose. But the point is, what it's trying to do is fit the green or the gray, these two models that you picked, as close as possible to this red line. Now, it's doing that so that by adjusting all of these parameters, this C, this C, this R, all the ones up here, this C, this R, blah, 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 all these parameters, it's going to keep adjusting them until it happens to get these values relatively close, okay? And sometimes what that means is it just happens to move this, this value here slightly, become slightly bigger. Like that's just the like it might appear to you like, why isn't it showing up right here? Why would it get bigger? Well, because statistically, when the green RU is slightly bigger, the difference in like the rest of the fit from here to here is slightly better. That might be it's math. It's not like perceptive the way you are when you're looking at it, and you're looking at it saying, hey, it's different, it's worse, it's better. You're able to look at it, in particular, usually the Nyquist plot, and say, hey, this doesn't look like it's in the right place. That's why, again, in our software, for instance, I don't know if I have like perfect data to show you here. But if you were to look at some data set, for example, I won't spend forever for circuit fitting, but just to kind of give you an example. I don't know. Let's just fit something simple really quick. So this is also what I mean by our software. See this high frequency area here. I don't really want to fit these data here. This is a part that I would say I don't really care about. So let me get rid of those first like bunch of data points. I don't really want to fit those ones. So let's just get a quick fit for this so we can just kind of talk about it. So my point is like here, it's trying to fit the red, right? Okay, well this doesn't look like it fits that well. Like this end part doesn't fit great, right? But it's like, it might just be, and if I zoom all the way in here, you can see, it's like, it's pretty close, but maybe in my mind, I might tell myself, hey, you know what? I bet the R should be like over here. Like this is a better R U, right? Like see how the red line, that lines up better with that first data point? But it put it here. Because it just so happens that when the math solved the equations, when it was over here, the rest of the, data fit better. So it's just algorithm. And by picking a different circuit, a different model, the calculus it changes. All the math changes entirely. Because now when you have a different model, all of the mathematics just change slightly, like maybe slightly, maybe aggressively, but the math changes. And so because of that, some of those values are going to be slightly different. They just are. Like this is the answer is somewhat mathematics, but I hope I've kind of showed you at least a little bit and tried to explain why. But it's really just the mathematics of the algorithm and circuit fitting itself that explains why you're seeing what you're seeing.
Nice.
So I know it's a bit long-winded, but I hope that kind of showed you with examples why you're seeing what you're seeing. I think there was a third part of their question.
There's a third part. Yeah, there's a third part of the question, which I think we can get to now. It's on something different, but
okay.
Some of the, well, I'll at least address a couple of things here, just going in order of when we received questions. I'm David16 says, how does the brain think and form memories? And I have no idea. I'm just going to leave it at that. Neil, do you have any idea?
So a little fairy flies around your head and it pours fairy dust into a bucket. And then the fairy dust gets processed, and it either gets processed into a memory, which goes over here, or it gets processed into an action, and that's what leads you to do things. So it's fairy dust.
Fairy dust.
Fairy dust that's processed into memories and actions, and that's how you do anything and remember anything. It's fairy dust.
Yeah, it's fairy
Science.
Yeah, science.
And that you can take that to the bank because I'm a neurologist for sure. That's definitely what I am. No, I have no idea. I have zero clue. I'm not a brain scientist. I have no idea. There's probably a technical answer involving neurons and synapses, and it probably does have to do with electricity in some sense, if you consider, stuff firing in the brain to be electricity in some sense. But I have no answer to that question. No real answer.
Yeah, I know about neurons and some of the synapses, but I don't know enough about those things to provide an answer that wouldn't be just mostly wrong.
Fairy dust is as good of an answer as any, I guess. We're gonna go with that.
All right, moving on. The next question. It's not actually a question. It's just interested to learn about bonding, hydrogen bonding.
What about it?
What do you want to know about hydrogen bonding? Not that I'd say I know a lot about it, but it's just the general idea is that it's just a form of bonding where if you have certain, I think it's, what is it, oxygen or fluorine. I know oxygen's the easiest one to know, but it's an intermolecular force that's stronger than van der Waals forces between molecules that have hydrogens on them, that are like O's and O's or
it's a strong polar bond, I guess is what you would call it. I guess
it's an intermolecular bond. It's an intermolecular bond, so it's a bond that it's not like a covalent bond. So in water, it's, what is it? So let's draw this. Let me revisit. Let's revisit Gen Chem for a minute, because
it's been a minute.
It's been a hot minute. So water is the kind of simplest example, but it's like, okay, you have oxygen. It's got these two lone pair electrons, and it's got two hydrogens that are bonded. And then let's say we have another. Oh, wait, hold on. I don't have to. There we go. Just make another one. And let's say there's another one there. So hydrogen bonding is this.
Oh yeah, it's the interaction.
It's the interaction between those, between this hydrogen and this oxygen, because there's a, there's a part, I call this like a partial positive charge, partial positive, and there's partial negative. And so those kind of interact with each other that give water some of its properties, like melting point, boiling point, at freezing points, things like that. So so it's not this bond, but it's this bond, and that's better than, say,
Van der Waals forces or something.
Yeah, Van der Waals forces. So I can't think of it like I think ammonia. I can't remember if ammonia has it, but like just nitrogen's the only molecule that's coming to mind. Like if you had nitrogens all over, and you had another nitrogen, there's just,
you don't get the same.
You don't get the same. There's no like, there's very weak Van der Waals electrostatics, because you're the only like partial positive and partial negative that's giving you an interaction between these nitrogens is based on random motion, like the randomness of the electron being in a certain position at a certain time, that creates the bonding between these. So this by chance, oxygen's way more electron negative, so the probability of having negative electronic density on the oxygen is pretty high, and the probability of having partial positive density on the hydrogen is pretty high, especially because it's pulling more. This bond is just two electrons, but really they're closer to the oxygen than the hydrogen. So this is mostly like a proton, in most cases. So therefore, statistically, you have more of this interaction happening, which is stronger than this interaction that's happening. So that's all I know about hydrogen. You now know everything that I know about hydrogen bonding.
So don't ask follow-up questions. That's all, everything that we know about hydrogen bonding.
I guess you could ask a follow-up question, but I wouldn't. I would be limited in helping you. So again, just going in the order in with which we've received questions. Murmur Salim 495 is asking at hand. One more question is that please explain why material gets oxidized and reduced at specific potential in CV. I guess there's I guess I can. Do you want me to talk about this?
This is like your potential window thing, kind of.
Yeah, I'm thinking like the question is, why is there?
I mean, it's
why
just
does
about
it get oxidized and reduced?
E0 basically. I don't know what other.
Oh yeah, actually,
maybe
I go into Nernst equation.
Yeah, so we got the Nernst equation in
already. Nernst equation.
Under an hour. Under an hour, we already got Nernst equation.
It wouldn't be, and here's the other thing. So this is episode 120. It wouldn't be a good, even episode number and end of the year without talking about the Nernst equation.
Well, also 120 is the number for the TAFL slot. I mean, it's 118, but 120 is the number for the TAFL slot. We haven't got a TAFL question yet.
Oh man, we missed two.
120 millivolts per decade. I mean, this is crazy. I can't believe we haven't even. Oh,
but should episode 118 have been the?
Technically, it's 118 point something or whatever, but everyone says 120.
Yeah, that's true. That's true.
Just like 57 or 59, it's technically 59 instead of 60. 60 and 120.
Oh yeah, for
TAFL, and then for the split, it's 57. But I just call everything 60 because I can never remember which is which.
Yeah, no, absolutely. All right, so let me just get back. His question specifically is about why material gets oxidized and reduced at a specific potential. So there is I'm going to describe a very kind of simple explanation or a way of thinking about this. So the description that we typically have, which is very simple and loses a little bit of accuracy, has to do with the kind of the molecular orbital MO theory, if you will, molecular orbital theory of molecules and atoms and stuff. And the idea is that when you have a molecule, at some point there will be a HOMO, a highest occupied molecular orbital, and that's got something like this, and maybe there's a few of them, something like that. And then there's a LUMO, which is the lowest unoccupied molecular orbital. And so there's some molecular orbitals above here, and there's some molecular orbitals below, but these are all full. These are all full. And then you have, of course, this whole scale is energy. So when you're taught this in a chemistry class, energy is the y-axis in this case. And this actually doesn't have like a position. Yeah, this doesn't have a x-axis value, if you will. Or maybe it does, and I just don't know what it is. And so when we think about an electron transfer, an oxidation and reduction reaction, we mostly think about this. We kind of forget about all this other stuff. And we think about the HOMO-LUMO gap. So when we have an electrode, at the electrode surface, so if I have this electrode, okay, some kind of conductive electrode, and then I have the HOMO-LUMO gap. Let's just say there's one electron there, and this is the HOMO, and this is the LUMO, of a molecule. So there's some molecule that has this. When there is this, I'm dealing with potential on one side, which sometimes is the symbol of E, but I'll make it just P. P for potential. P for potential. So there's a potential, and then there's an energy. But these are they're very similar because they're related by the quote electrochemical potential of your redox reaction, so to say. So they're related. Potential and energy are related. We're not going to get into that now. But all that's to say is that when the potential of the electrode matches that of the HOMO, depending on what's there, if the energetics are correct, you'll have electron transfer between the kind of the occupied or the unoccupied orbitals of your molecule with kind of what we would call the filled states. So in an electrode, you have a density of states, DOS, in your electrode, and you can have electrons jump back and forth. And from the molecule's perspective, it has everything to do with what's the energy of the HOMO-LUMO on this kind of absolute energy scale. That's kind of what causes oxidation and reduction reaction. Sometimes the HOMO is full and you don't have an electron going this way, you have an electron going the other way, right? Or maybe it's in the LUMO and it goes this way. Right. So that, I think that hopefully that kind of answers the question. It can definitely get much more complicated, because even the HOMO-LUMO, which is described as a discrete energy level, well, that's a discrete energy level if you have like a single atom, or a single molecule in the gas phase. But in solution, and especially in solution with different kinds of solvent molecules, you actually have a distribution of energy states where you can have electrons moving back and forth between the molecule and the energy of the electrode. So that's so we say that like, oh, it's a specific potential, but really when you think about it, there's current flowing way before you hit the redox potential, and I guess that goes back to the Nernst equation, which is that you actually, even though we get this number, a potential in E naught, you can still have electron transfer because this represents the equilibrium condition. And if the kinetics are fast, you'll get current to flow to adjust this ratio of the oxidized and reduced species such that the potential matches the Nernst equation for a Nernstian system. So maybe that was a little bit too much. I think things can definitely get more complicated. But hopefully that answers your question. Of course, we can talk more about it later if you want to.
That's like the basic theory answer for why the stuff happens.
Yeah. And it's very basic. I think it's actually a little more complicated because there's a lot, people, some of the next questions we're getting at are like oxygen evolution reaction and hydrogen evolution reaction, and those involve bond breaking. And this model does not have anything to do with bonds being formed or broken. Like, to my knowledge, I don't know if anyone thinks or talks about that kind of stuff.
Well, speaking of bonds breaking, Greed Gaming has asked about OER and HER. It says, is it possible to make a perfect EDLC, electrochemical double layer capacitance device with no faradaic current and a OER HER? So to be clear, I guess I don't understand the second part. Are you saying no faradaic current and no OER and HER, or with no faradaic current, but you do have oxygen evolution or hydrogen evolution reaction? Because those are contradictory statements.
Yeah.
Because if you have OER and HER, then you have faradaic current. It sounds like you're saying you would have no faradaic reactions at all, which includes OER or HER. So you'd have neither of those. That's what I'm assuming you mean, because again, it doesn't make any sense. If you have OER or HER present, then you have faradaic current. Is it possible to make a perfect device?
I think we need to know what perfect means.
What do you mean by perfect? Yeah, I don't know.
Yeah.
I mean, people make first of all, I'm not even sure what you would be looking to accomplish. So people make supercapacitors. People study supercapacitors, like materials for supercapacitors, for instance. And the benefit of those is that they have a lot of capacitance. In case you couldn't tell by the name, the electrical double layer is not a very large capacitor. In fact, it's a very small capacitor. So I don't really know what the purpose of a device would be that operates entirely and solely on the electrical double layer. I'm not sure what purpose it would serve.
Just a short charge, just another kind of capacitor, right?
Yeah, you could for sure, but the amount of charge you can store on the electrical double layers is minute. In the grand scheme of things, right? It's pretty small.
Well, it's bigger than traditional. I think the theory behind some supercapacitors is to utilize double layers, because you could probably in a device, you could have a bunch of, I think I'm forgetting, but like you can either pack them in parallel or series and dramatically increase the capacitance, but it's because it's all electrolytic.
Yeah.
And if you just have lots and lots of these together, you can have huge capacitors in a much smaller space.
Yeah, that
So
makes sense. I guess
that's the, but
if
yeah,
you have enough surface too,
yeah, if
if
you
you have
have
enough
enough
surface
surface,
area.
and if you design the device so that you put lots of thin layers next to each other in parallel. Let me remember. Like
If you put them in parallel,
yeah,
the current when you put devices in parallel, the voltage is the same. The current adds up. So if the current adds up because current is equal to capacitance times voltage, if the current goes up, the capacitance will go up. So if you put them in parallel, you'll get more capacitance in theory.
okay, all right. So capacitors in parallel
You get more capacitance.
should give you more capacitance.
I believe
Okay,
that's
all
correct.
right.
The opposite
Okay,
would happen if you put them in
yes,
series. If you put them in series, you would actually divide the capacitance. It would go down
it would go
because
down.
the
Yes.
voltage would increase,
Mhm.
which means it would be less per capacitor. The voltage goes up, that means C goes down because the current remains the same.
Yeah. So in that
So,
case, you could make so if you because you can imagine someone could take electrical double layers, just really really thin electrodes next to each other, and
yeah,
just stack them,
yeah, all in
and in
parallel.
principle, keep adding even because you're right. One electrical double layer on like a glassy carbon electrode's got like
Yeah,
microfarads of capacitance
or less. Yeah,
or
whatever.
less.
Yeah,
But if you scaled it up and then stacked them really thin next to each other, then you could in principle get a lot of capacitance considering quote traditional capacitors that we see.
yeah. You could think about it as like fins, like you could have like a bunch of fins, almost like a
Yeah.
radiator or something. If you have like a bunch of fins, and every two of them is connected in to a system, to a circuit, every
Mhm.
two, and so you connect all of those in parallel,
Yeah.
right? That's how that would work. And so you would put all those in parallel, and you get a tremendous, if it's enough surface area, um, then yeah, then in theory you would get a lot of capacitance, and you could use it as a charge storage device. So
Yeah.
yeah, it certainly could work.
Yeah. And perfect is always, of course, depending on what the needs are. But I think what he
Yeah,
means is like there's no faradaic current.
yeah, and that'd be perfectly possible. He says I'm researching supercap devices using carbon
Mhm.
electrodes, almost exclusively form pseudocapacitors. So I was curious if it's possible. Yeah, it should be still possible. Um, Pseudocapacitance or otherwise, you still should be able to get enough, um, you know, material basically, as long as you have enough surface area, basically enough material to um, generate some capacitance, which can lead to charge storage for sure.
Yeah. And the voltage itself, yes, you can create different kinds of. I've actually learned there's lots of different types of like carbon. There's like glassy carbon, and then there's diamond. There's these things like boron dope diamond, and there's other types of I think it's called diamond-like carbon, which is it's like less conductive, but or it has a very large potential window. So in a way, it's like as long as there were no redox reactions, it's not very catalytic to oxygen evolution or hydrogen evolution, and you can actually get a lot of charge, form a lot of double layer charging within a pretty big voltage range. So I think carbon does have a lot of there is more research or things that can be done in terms of carbon being used for supercapacitors that are not pseudo capacitors in the sense that they also have a faradaic reaction involved in the charge storage. But yeah, that's my 2 cents. Recently learned about some of that.
All right,
Okay.
let's see. I think Vaji
Yeah.
Hisalidi says,
Mm-hmm.
can we rely on the counter electrode cathode in an alkaline electrolyzer? Counter electrode cathode. Okay, that checks out.
Mm-hmm.
As a reference electrode and obtain two electrode CV? Yes, you can. Is the voltage stable if both electrodes' geometric area is the same? Why would that be a problem?
So if they're passing a lot of current and the electrode area is the same, well, oh, okay. So typically in like traditional three electrode systems, the counter electrode is supposed to have a larger surface area. And that is because the counter and working need to have the same amount of charge, whether it's oxidation reduction reaction or even formation of double layer. If the counter electrode were to have, say, a smaller area than the working, you need a lot more charge in a smaller area of the counter, which means that the voltage of the counter electrode necessarily changes a lot. But if you have a huge area counter electrode, then when you pass a lot of charge, well, it's spread out across this very large area. You're not forming these big voltage differences. So when the area is about the same, then if you're applying a lot of current, milliamps or higher, if it's microamps, maybe it doesn't matter. Then you may have, you may observe these bigger voltage changes with your counter electrode, especially when it's acting as the reference. If that makes sense. Does that make sense?
I think it makes sense.
Yeah. So yeah, if that's the case, I mean, I've even told people, like, even if you have a working and a counter electrode, and you want to use the counter as a reference electrode as well, if you can just minimize the surface area, the exposed surface area of your working electrode, that's enough that it's like, oh, the counter doesn't have to build up as much. It'll still have to build up the same amount of charge, but the voltage doesn't actually change as much, so it ends up being more stable. Will it be like a true reference electrode? Probably not, but it depends. It depends on how much current you're pushing through the system. Especially if you have like an electrolyzer, then maybe you actually have a lot of current. That's my thought.
Yeah, but this is also common, I would say, as a general rule of thumb for both electrolyzers and fuel cells. It's pretty common to have a two electrode setup, and both electrodes usually have the same geometric area sort of by design, mainly because if one has assuming both sides, a lot of times they're the same, a lot of times it's like platinum on carbon or something like that. It can be different if you have different materials on the anode or the cathode and they have different activities or whatever. But assuming you have like the same, let's just say roughly the same material on both sides of your electrolyzer or fuel cell, and you're trying to match capacity of both sides, you usually try to have the same area, because if you had different, in this case, if you're following the logic like Alex was just talking about, where you're sort of thinking, oh well, if my counter electrode commonly has a larger surface area to help generate the current or generate the completing the circuit that I want in a three electrode system. Well, in a two electrode system, like an electrolyzer or a fuel cell, you don't want to have one side be way bigger than the other side because it's wasted. Because you'd have like a huge amount of surface area, huge amount of extra area. But that would be like in a three electrode system, it's wasted, but it's okay because that's what the counter electrode is there for. In a two electrode system, in a fuel cell or an electrolyzer, it's not the same situation, right? Your anode and your cathode are essential parts of the device, and because of that, you're already the name of the game. At least in a lot of the research with these devices is to try to improve the longevity, reduce the amount of platinum we use because it's expensive, improve its adherence to carbon so it doesn't fall off or agglomerate over time. There's a bunch of stuff like that. And so if we're throwing a huge amount of extra platinum into the cathode or the anode, whichever side, in an attempt to, I guess, try to improve this aspect of electrochemistry, which is, having enough surface area at the counter electrode. All it really means in the context of an electrolyzer or a fuel cell is that you're wasting material, and providing way more than you need on one side, which can serve a purpose. For instance, in a fuel cell or electrolyzer, your one side is always the rate limiting side, basically. So in an electrolyzer, the anode is the rate limiting side. In a fuel cell, it's the cathode. But the extra material is not generally going to change those kinds of things. It's like the device. Same thing with a battery. Sort of, you're limited by the side that has a smaller capacity. It's like if you have same with a capacitor. If you have like two parallel plates, you can think about it, and one plate is like this long, and one plate is as long as my hand. Well, the capacitor is only going to be this much. All the rest of my arm is useless. You can cut it off. It's not needed. Please don't cut my arm off. But you know what I mean? Like, so like, you might as well make the second electrode my hand also, because these are the same size. It can only store charge over this amount of area. So if I have all this extra area, all this extra material, it's just wasted, because whatever's the small, if this is the amount of area, this is still too big. It's all too big. It's like, now this is the same area. It's matching, right? So like, whatever the smallest area is the one that you want to match it with, in a two electrode device, basically. So you can look at it that way, and then you can sort of work onward from the idea about, well, what's the voltage? Is it stable? I mean, you can have issues no matter what with the voltage in a two electrode device, regardless, because you don't know what the individual potentials are of either side, because you don't have a reference. But usually when a device like this, it works out okay, I guess I'd say, very broadly speaking, without having to have a reference electrode, because you're primarily concerned with the voltage anyway, because that's what the device is there for. It has a voltage, and you change the voltage to put energy into it. That's how it works.
Nice. Yeah, I was just thinking about it from a pure like 3 electrode electroanalytical system, not from like a device perspective. You're
no,
right.
it's what you were putting was obviously out there was correct. It's not that, it was just it's a bit of a weird thing, I guess, that as what you were saying, and then I'm thinking about it, it's like it's a bit of an odd situation to consider, that it's like the I don't know what you'd call it, like the discrepancy between having a large extra area in a 3 electrode system is desirable.
Yeah.
And in a 2 electrode system, because of the area matchup thing, basically, it's totally not what you
desirable.
want. You want the areas to match.
Yeah.
And it's like, oh, because in one case it's wasted.
Yeah. Yeah. Exactly.
And it's like, well, it is wasted in a 3 electrode system. Your massive platinum mesh or whatever, or platinum coil with all this surface area, it's wasted.
Yeah.
But it's by design.
By design.
Yeah, it's by design wasted. It's just we don't call it wasted. We sort of call it like, a big enough area to make sure that it gives us what we need or whatever.
Yeah.
But it's like, it's not that doesn't help, because so much of that surface area basically isn't needed. We just have it as a fail-safe kind of a thing.
Yeah, no, exactly. You don't, if you're studying just like a reaction on the working electrode, you don't want the counter electrode reaction to limit you. So you just make sure everything on the counter electrode's like great and catalytic, and that's why I use expensive platinum. But no, in a device, you're right. It's like, oh yeah, it needs to be optimized so that they're both equal areas. Otherwise, it is wasted. So we have a comment from Barry. We haven't seen Barry in a while. Hey guys, I quit academia, so I haven't been around in a while. Just wanted to let you know you helped me with 3 publications. Fantastic. And a few more waiting for submission from collaborators. You guys are good. Thank you, Barry. Thank you.
Cool.
Really,
well, you quit academia. That's the best part of this.
That's the best part of this. Yeah. And but yeah, thanks for stopping by. I guess we might not see you around too much then, because if you quit academia, there's no point. Well, I guess there's a point if you're in industry and you're studying some corrosion thing or a battery thing. You can always still, mostly academics contact us, but industry folks can also talk to us about stuff if it's not proprietary. But
yeah, I think awesome. most of our audience is probably academics, but I'm sure there's some industry people.
Yeah.
Maybe some corrosion people, maybe some battery people. I don't know.
Yeah.
We don't generally get biographical details from the random YouTube usernames,
Yes, that's right.
Can't exactly infer tons of information always. Doesn't always get you very far.
Yeah. Well, Barry, we hope that you have a happy holidays and that you're doing well. Thanks for stopping by the stream.
Yeah.
All right. It looks like we don't have any questions right now, or any that are in the pipeline. I guess we'll just take this quick moment to at least just remind people that over the next 2 weeks we'll be out. There are 2 U.S. holidays that are coming up, Christmas and New Year's. A lot of people are on vacation and take time off. We encourage you to try going outside and being, spending time with family and stuff like that. So yeah, just a reminder, but if you stay tuned to us on LinkedIn and YouTube, you will see upcoming notifications for live streams. And we'll probably get started back again after the new year. So just keep that as a heads up, and we'll usually make some announcements as well about upcoming things that Pine is doing. I think there's a lot of stuff in the pipeline that we're hoping for, preparing for. Barry's saying he's gonna play some Battlefield 6. That's awesome.
Moved into the mountains, never coming back. Yeah,
it's awesome. Awesome.
Well, good for you. Get away and never come back. He's gone. He's gone forever.
He's gone forever.
Enjoying life far more than most of us, I'm sure.
Yeah.
Good for you, Barry.
All right.
Enjoy your seclusion.
Yes. All right. Well, do you think we should call it? If there hasn't been any, or if you have any other things that you want to say, or
there was that one question about Mott-Schottky and PN junctions. Okay. If I want to talk about it, I can.
Yes. If you want to.
Yeah, I can talk about this a little bit. There was this. I know it's from like several weeks ago, maybe, but I did a webinar with Mott-Schottky some time ago, and somebody had asked a question. I think it was on Livestream, but so how did a PN junction look in Mott-Schottky analysis? Which is a good question. I mean, I guess when you think about Mott-Schottky analysis, I showed in my webinar, or at least the theory of how bands bend for P and N-type semiconductors, and then how the Mott-Schottky equation works and everything. The ironic thing is that during the webinar, I did my live experiment on a solar cell, which is a PN junction, while kind of not acknowledging that I was doing that. I just did it anyway. And the reason I did that is because I've found it very difficult to find repeatable P or N type semiconductors that I can do here in my office, where I'm somewhat limited by just life, and I don't have a great research lab at my disposal like everyone except Barry has now, in academia, where you have a lab and you probably have nice N and P type semiconductors at your disposal. So solar cells work quite nice.
PN junctions always from these oxide layers, and you need HF. You need
Oh, that's
HF
right.
to get that off. That's why you can never put this in the,
That's right,
in
because
our
I don't,
office.
because not only do I not have hydrofluoric acid, I refuse to work with it categorically
Yeah.
because I don't want to die.
Yeah, that's right.
HF scares the ever loving crap out of me. I'm not gonna lie. I have no desire to ever be in the same universe as HF. It just always scared me. I learned what it does to you. It gets into your bones and dissolves your bones, and then you die before you realize what's happening.
Yes.
That's not fun.
Not good.
You know.
No.
But anyway, if that's the reason that I can't ever get a real N-P-type semiconductor, I'm okay with it.
Yes.
But more to the point, which is not about dissolving bones, a PN junction is an interesting kind of a situation. So I'll just draw a few things and kind of illustrate this, and then if there are any questions, we'll get to them after this. If there are no more questions, then we'll sort of call it after this. But if we look at an N-type semiconductor, first of all, an N-type semiconductor has, this is supposed to be a rectangle, and my drawing skills are fading as my brain apparently is. This is the conduction band, okay, and this is the valence band. All right, my Fermi level's up here for an N-type semiconductor, because I basically have a little bit of this filled. Okay, blah, 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 and this whole thing is filled. All right, and a P-type, I should have put a dash in there, but I didn't. So I'm gonna put it in there. P-type, you can tell I'm slightly delirious. I hope this is at least entertaining.
Oh, this is great.
Conduction band and valence band is down here. And for a P-type semiconductor, we have an excess of holes, which means that it's not totally full in the valence band, blah, 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 blah. And our Fermi level is down here, slightly above, not on it, because I can't draw. It's great. All right, so when I put these together, the default condition of a PN junction looks something like this. The Fermi level is going to be constant throughout. So you have to think to yourself, how does that work if the Fermi level is the same throughout, right? Well, if the P is over here, the Fermi level is just above the valence band, which means the valence band for the P part is going to be here. I'm going to draw this open-ended because I'm going to connect them, okay? And the conduction band is going to be up here, right? And if I draw it on the right, so that it's PN junction, so P over on this side and N on this side, right? And now if it's on the N side, the Fermi level is right below the conduction band. So the N conduction band's got to be over down here, right? I shouldn't draw it as high. It should be like down here or something. Trying to draw the geometry a little bit accurately, right? Okay, so this is where they're going to start. Now, there's a junction, right? So that's the key here. So sometimes you can draw these bent. Sometimes people draw them straight. I'm not really sure. There's probably logic behind why you draw one the other. It's probably going to bend a little bit like this. So it's kind of a band bending at the junction, but this is what we call the depletion layer. And this is what it looks like in the band perspective. This should have been lower, so I could have drawn more room to go, but oh well. Okay, so this is the PN junction. This is what it kind of looks like. And this region right here is what we call the depletion region. Depletion layer. Okay. And so another way to think about this is in the depletion layer, I'll draw a different kind of diagram for you, is that we have our P-type semiconductor and our N-type semiconductor. I'm not going to draw bands now. I'm just going to draw the P-type semiconductor. We have this P-type semiconductor here, and we have this N-type semiconductor here, okay? The P-type semiconductor has extra holes in it, right? It has extra holes, positive charges. The N-type has extra electrons. It's got extra negatives hanging around, right? And what we get is this depletion region, that forms right at the interface. It's where those bands are bending that I just drew. Those are supposed to be straight lines, but I'm dying. So that is where the electrons and the holes combine, and it's effectively neutral. So this is kind of a neutral-ish region, this depletion region. Okay, it's kind of neutral. And so what we have is when light shines onto this region, okay, we have a situation which is that the light provides enough energy to release some of these pairs. So the electrons that came from here into the region and the holes that came into here, they made a neutral. The light jars them back free. Okay, and what it does is it actually sends the electrons back towards the N-type. It sends the holes back towards the P-type. Okay, and if we connect this thing to a circuit and we measure the voltage, I should have drawn that open, but I didn't. We measure the voltage of this at we'll get a potential associated with this, basically, right? Because we have a distribution of charge, and so we get a voltage. Okay, now how does this work for Mott-Schottky, right? The tricky thing is that let me draw the diagram really quickly here. So if this is voltage and this is current, you can think about it as a CV. This is the open circuit voltage. It's some value, right here. When light is shining on it, we have some voltage here, and if there's no current passing, that's the highest voltage it can get. If I connect the P and the N to an external circuit, and there's nothing here, it's just open, it's totally zero resistance, and I allow current to flow, it flows in this direction. Okay, the maximum amount of current that I can get out of this is like the max current. It's some value depending on how much sunlight is shining on it. Basically, as you can imagine, a solar cell gives you more current if there's a really sunny day, and if it's not a sunny day, it gives you crappy current. So kind of makes sense intuitively. And so there's some curve that goes between these two, right? So as the voltage goes from the open circuit value to 0, this is 0, obviously, my current, it's just typically negative based on convention, because this is the working electrodes on the P, the counter electrodes on the N, basically, are the reference. So the current is just by definition negative. You could look at it as positive. It doesn't really matter. It's just a direction thing. So as we go from 0 to I max or minus I max, whatever, we are dropping the voltage. Now here's where the Mott-Schottky becomes kind of bizarre, right? For Mott-Schottky, we're looking at band bending, right? And for this, it's like we're talking about moving the Fermi level up or down, right? When we move the Fermi level up or down to bend the bands for the N-type, I'm going to draw this wrong. The Fermi level goes down. You get that. This kind of situation with the Fermi level going down. If the Fermi level goes up for the P-type, something like this. So the bands bend like this, right? And so the same thing's going to happen. I'm not going to draw it because I'll butcher it like crazy. But a similar thing happens basically when you. This is easier to conceptualize in this world of standalone N-type or P-type. As part of my webinar, I showed this, and it was a little bit easier to kind of conceptualize how these things bend. With the P-N junction, it's just more complicated. The Fermi level will split between the P and the N side. Both of them will bend depending on whether you forward or reverse bias it, and you'll get this middle part will either be way more aggressively bent like this, basically, or it'll be more gradual, something like that. So the difference, like this, this part here, will be either like really, really aggressively bent or not as aggressively bent. And your Fermi levels will be different. Like instead of being the same across at equilibrium or whatever, like flat band here. Okay. Now the tricky thing is, and I could be wrong about this, and I'm not an expert on this topic, so apologies if this explanation is not correct. It's possible this isn't true, but I think it's largely true, which is that to back up for a second, the flat band potential here, this situation for my N and P type semiconductor, this is the flat band like situation where the Fermi level is flat. That's not necessarily the measured open circuit potential in a 3-electrode system. It's not. It's not necessarily OCP. So people can make that mistake. It's some value, but it's not necessarily OCP. That could be different. I think, again, I sort of hesitate to say this, but for some reason, I think it might be true that the open circuit, when you're measuring a PN junction as a 2-electrode system, I think that is the flat band. So like for a solar cell, I believe that this VOC is likely your flat band potential as well. So in some ways it's tricky, but in some ways it's easier because the Mott-Schottky involves taking your flat band potential and going away from it to bend the bands so you can measure the space charge capacitance. Well, if you don't know the flat band potential, it can make it difficult. Well, how do I move the Fermi level if I don't know where it is to begin with? So you have to usually measure, figure out where it is, and then do another experiment to like verify that what you measured was correct. It can be tricky. In a solar cell, let's say we assume that this is, let's just say that this is roughly the flat band potential. Okay, so then what we can do is we can lower the potential from the open circuit potential, open circuit voltage, whatever. In this case, we'd be getting current out of it, and then we can do our impedance along the way and do our Mott-Schottky measurement. Now, here's where the tricky part is. It really will depend on the device, and I'm not sure I have a perfect answer for like what does the Mott-Schottky exactly look like. I have one example from, for instance, when I was somehow in the past able to get Mott-Schottky data on like a P-type semiconductor, you'll see that I got this plot. I think I had an N-type one. Where is it? Yes, Mott, and this one. I had some of this, a little bit funky. You can see it kind of goes up, and then there's multiple regions. I'm not going to explain this too much. I can explain it if someone's interested, but there's some reasons why. For example, the slope changes and stuff like that. But I don't want to get into that. It's more than I want to explain in this particular instance. In some ways, the answer to the question of how does the Mott-Schottky look in a PN junction is it can be the same. It at least can be similar. You can get similar kinds of diagrams. But this in particular, you see where I have a negative slope? This is a Mott-Schottky plot of a P-type semiconductor. This is a negative slope, okay? And one of the aspects of a real Mott-Schottky, a real PN junction, like a solar cell, is that very often the P-type semiconductor is actually physically thicker. So that's why in this case, like this is a slide that I have shown before during one of my impedance webinars, I think. But I animate and show how the solar cell works. But I drew it this way where the N-type is here and the P-type is down here. But I drew the P-type thicker. That wasn't an accident. It's because P-type semiconductors are actually apparently thicker, like boron doped silicon. There's reasons for that, but basically as it relates to Mott-Schottky, as far as I can tell, what one of the results of that is that the Mott-Schottky of your solar cell looks something like this. So it behaves like a P-type semiconductor because P-type semiconductors have negative slopes. N-type semiconductors have positive slopes. So what's tricky about it is that the bands are bending and all this kind of stuff is happening like I was drawing. But I'm basically only measuring the Mott-Schottky parameters for like the electron donor density of the p-type 1. And as best I can tell from some literature study and a little bit, you know, I'm not 100% sure. To be honest, I'm not sure there's a lot of discussion on this, and maybe there is in the literature and I just haven't found it. It's possible. But it's like the side of the p-n junction, the p or the n, I suppose, that's more dominant, might be the one that you measure. Now, in the case of your p-n junctions more equally split, if you will, you might be able to measure both. And so you might end up with, for example, a Mott-Schottky plot for a p-n junction that's like this. So like here, you're measuring the n, and you know here you're measuring the p, because the negative slope will be the p-type side and the positive slope will be the n-type side. So that's something you can get. With a solar cell, I'm only able to measure the p side, right? Because as I said, it's thicker. I think it kind of seems to sort of almost negate the ability to measure the n-type side for this particular example. It might be that it's so much thicker that it just makes the n-type 1 negligible or something like that. I don't 100% know the reason, to be perfectly honest. But I hope that kind of explains a little bit of it. I know it's kind of complicated, and my ability to draw is lacking at best, let's just say. But this is roughly in line with what you would expect to see for these kinds of systems, and what you might expect to see for the Mott-Schottky diagrams, depending on you know, what kind of system you have, I guess. So,
All
so there you
right.
go.
There you go. So there was one question that came in while you were describing that, which is on how does Latimer diagrams work? I did a quick search. I haven't done Latimer diagrams since inorganic chemistry in college, which perhaps just goes to show you how maybe, I don't know how often they are used. But a Latimer diagram, it's basically, you may have, let's just say, some chemical substance, let's just call it A, and then it goes to maybe, you know, A and some, you know, some other species, let's call it X, and then it goes to A with another, you know, let's just call it like 2X or something like that. And at each stage, there would be a different oxidation state of A. So for example, if this is A plus 1 and X is maybe a, you know, it's like maybe X has a minus charge on it, or actually no, maybe this is neutral, this is 0, and this is A in the plus 1 oxidation state, this is A in the plus 2 oxidation state. And then there'd be like some kind of voltages. Maybe it's like plus 0.102 and then plus 0.05 or something like that voltage. And there may be different pathways for A to go from here to here, and there's like, you know, maybe it's plus 1.152 or something like that. You know, other mechanisms, but basically, Latimer diagrams are similar to Poor-Bay diagrams. So this is a Latimer diagram, generic one, Latimer. But then there's also something called Poor-Bay. And they're similar in the sense that this describes the oxidation state of whatever the compound is. And so it's not necessarily, oh, electrochemically, I was able to go from, you know, to create the +2 species. It also has to do with the pH or the system, you know, whatever is required to get the oxidation state of A to be in this state or in the -1 state or something like that, or the +2 state. You'll end up having you know, it may be connected to a variety of different molecules, and it will exist in different forms. So, you know, for example, let's see, what's a good example? Well, I just went online to find some examples, but like nitrogen, for example, nitrogen gas. Yeah, here we go. So like nitrogen gas, N2 as the zero oxidation state. But I think it's in the +1 oxidation state when it's in N2O, right? So it's a different like chemical phase, but we're just looking at nitrogen, the oxidation state of nitrogen. And so it's a different species overall, but you're looking at different oxidation states in different like pH systems to give you these different states and what the voltages going from one to the other. And these voltages may be determined electrochemically, but they're purely thermodynamic type of things. So that's basically what a Latimer diagram is, and it can be extended for a wide variety of different types of systems. But that's like that's the gist of it. Honestly, I don't know much more besides them. I guess if I was teaching a class, I'd do more research on why they're useful and things like that. But that is the gist of a Latimer diagram.
It's funny. I don't think I ever used those. I definitely used Porbet diagrams when I was in grad school. I don't remember Latimer diagrams. Probably seen them before, but
you've probably seen them. They convey similar information because you can have, Porbet diagram has the pH and the potential broken down into a phase, and this just shows you on a line. Oh, it's this phase. It looks like this in this phase. At this potential, it looks like this at this phase. Or it exists like this at this potential and at this voltage. It's just another way of conveying, I think, some of the same information. Or similar information. It looks good.
Yeah, it makes sense.
Yeah. All right. Well, it looks like those are all the questions.
Looks like everybody's on holiday already, which is good.
Yes.
So, makes sense.
So I guess with that said, we'll call it a day. We hope you all have a happy holidays and stay safe. Good to yourselves. Relax.
That's right. Take some time off. Don't let grad school beat you down, unless it already has. In which case, our condolences.
Or you should be like Barry and go into the mountains.
Quit academia. That's right. We on more than one occasion for various podcasts and joke-like videos, we have recommended quitting academia.
And he did.
That's right.
Or at least maybe he defended.
I don't know. I hope he defended when he says he quit academia. But it sounds like he's just living like a hermit in the mountains, which all the power to you, I guess.
Oh yeah. I mean, he got 3 publications and he's submitting some others with collaborators. That's usually enough to.
Sure. Why not? All the power to you, Barry. Well, I agree. Happy holidays, everybody, and Happy New Year. And I hope everybody has a great rest of their December. We're going to see everybody in the new year. January 9th, I think, is the date. So.
I think so. I think that's the date.
And until then, it's been a good. We've been doing these for like more than 2 years now. So
yes.
As always,
I will continue doing them.
Thank you, everybody, for another year of successful question asking and answering. Well, you've successfully asked questions. I hope we've successfly answered them. We're doing our best.
Yes. Yeah.
And we appreciate everybody's support as always for our YouTube efforts. And I hope everybody has a great happy holidays, happy New Year, and we'll see everybody next year.
Bye.